Here I'm using the simulations created by Tom Greenbow of Iowa State. I'm putting a bar of zinc metal in a solution of copper nitrate. And what I want to look at is the molecular scale depiction of this reaction. Water molecules and nitrate ions are not shown. So here are copper ions contacting the piece of zinc metal. Copper ion moving because it's aqueous, receiving electrons from the zinc metal. There were two collisions in this animation, and the percent that were productive is 100%. Each collision of the copper ion resulted in a reaction. That's not really realistic. Now I'll do a different simulation which has a different percent productivity. I'll take a copper bar, put it in magnesium nitrate solution. So here are the magnesium ions that are mobile because they're aqueous. Here's the copper metal, which is solid and immobile. Here you can see lots of collisions. The magnesium ions are frequently bouncing into the copper metal, but none of these collisions are productive. 0% are productive collisions. That's also not realistic. So what we have to imagine instead is something between the two extremes. So reactions that occur will have some probability of productive collisions. Maybe it's 2% of the collisions are productive, which would mean that in this model here, you could imagine if there were 100 collisions, maybe 2 of them actually result in a reaction. So the idea that there are 2 factors in the collision-based model for chemical kinetics. One is how frequently do the collisions occur. If there are no collisions, you can't have a reaction. If the ion never meets the metal, you can't have a reaction. But the second factor, which is very important, is what percentage or what fraction of those collisions actually do result in reaction. And that's typically a small percentage. So here I'm going back to the copper and zinc model. This reaction does occur, but it doesn't occur with 100% of the collisions. So we have to imagine that perhaps many of the copper ions simply bounce off the zinc surface. The ones that do react, those are the ones we care about, but it won't be 100% of the time. Perhaps this one should bounce off without reacting, without undergoing electron transfer. That will make it a slower reaction than this implies. If only a fraction of the collisions are productive, the reaction rate will be slower. Let's look at a few examples, mathematical examples, of what this might mean. So here's the first line. Collision rate 200 per second. You can imagine that. The little bouncing balls collide 200 times per second. And if every single one of those collisions was productive, then the reaction rate would be 200 reactions per second. That would be a pretty fast rate based on our model. The second line here asks you to imagine now, what if it was the same collision rate, but only 10% were productive? So that would mean 90% of the time the atoms or ions just bounce off, no reaction. This will slow the reaction rate down to 20 reactions per second. That should make sense to you mathematically. 10% of 200 is 20. So 180 collisions occur per second with no reaction. This next one I'm hoping you can do on your own. If there were only 2 collisions per second, so now much slower. We have to kind of wait for them to collide. 50% were productive. You should know the number here. It'll be 1 reaction per second. Let's make up another number here, easy numbers. How about 100 per second? And a 5% productivity. So this is actually still way too high to be realistic. Most collisions are not productive in most reactions, so it's rare to have a productivity percentage that's as high as 5%. But you should be able to calculate it. If 5% of those collisions are productive, this is 5 reactions per second. I'm going to skip the next line. You can do that. You can make up your own. Make up your own. But down here, let's imagine that you can kind of see these 2 feed into 1. Let's imagine that we get 10 reactions per second. And it turns out this value here, the reaction rate, is the only one you can measure experimentally. You can look at the formation of product, maybe with a color change, maybe by weighing your product, or maybe by looking at the production of gas, how many bubbles are formed, or what's the volume of gas. That's a measurable reaction rate. That's something you can see and measure in the lab. These other numbers here, you can't measure those directly. But we can see that with this 10 reactions per second, it could be 2 very different situations. It could be that we actually get few collisions, but they're pretty productive. Or we could have a vast number of reactions. We could have a vast number of collisions, not a vast number of reactions, but a vast number of collisions. But a small percentage of those actually result in reaction. So you can see both of these green conditions result in the same measurable or observable result. And so this is sometimes detective work to figure out what went wrong here. Why was this reaction slow? Was it because the collision rate was low, or was it because the percentage of collisions that were productive was low?